Welcome to Operating Systems lecture 17. So far we have looked at how the kernel initializes itself and initializes the address space, and so we have seen that the kernel basically initializes the address space such that it firstly starts itself as at kern base, which on xv6 is this address hexadecimal 8 and 7 zeros, so it is 2 GB, right. It's a 32-bit address space, so it's right in the middle of the 4 GB address space on 32 bits. The first 1 MB is for low memory devices, it just maps it one to one to the physical memory. In fact, the entire space here till from kern base to kern base plus fizstop is mapped 1 to 1 to physical memory from 0 to fizstop, right. It loads the kernel's code and data in this area, right, and the rest of the space which is available from this space onwards is what's called its heap, and that heap is managed using these functions called kalloc and kfree, right. So if I want to allocate some space, I will call kalloc and it will allocate a page from this space for me, and that page I can safely assume that will not be overwritten by anybody else, and then kfree is adding that page back to the free list so that it can be used, so memory can be reused, and that way you can sort of not run out of memory. And this lower address space from 0 till kern base is reserved for user processes. So far we haven't seen any user processes, but now we are going to talk about how user processes are created, loaded and all that. We already have some idea. The user process will be executing in this space, so the user processes code and data will live in this space, the user processes stack will live in this space, and user processes heap will also live in this space, right. If a user ever makes a system call, it will be executed like as a software interrupt instruction, and the software interrupt instruction will dereference the IDT through the IDTR register, and from that it will get the address of the handler. The kernel will set up the IDT in such a way that all the handlers are pointing in the kernel's code and data region, so the handler will execute in kernel mode, right, with kernel's privileges, right. So the CS in the IDT will also say that execute this particular handler in privileged mode, right. So this is how things are going to work from now on and forever, really, right, as long as the system is going on, right. If I have to sort of show this in more detail, let's say there were two different processes, both of them will have the same kernel mapped. So let's say this is kernel and kernel, so above kern base they have the same area mapped identically, right, from kern base to kern base plus fizstop, same thing. So the entire physical memory is mapped. Of course the process cannot access it directly because these are privileged pages, and only code that's executing in privileged mode can ever touch these pages, right. So if a process is executing here, it may have different processes may have different mappings. For example, in these red lines here in process P1, let's say this page is mapped and this page is mapped, and in this process P2 let's say this page is mapped, so they have different address spaces in that sense, right, and they are completely independent address spaces. Also note that these pages which are present in the address space of the user are also coming from the physical memory, right, and the physical memory is also mapped in the kernel space. So the same pages in physical memory have two mappings in the virtual address space, one in the user side of things and another in the kernel side of things, right. Also, where will these pages be allocated from? From the kernel's heap, right. So there is the kernel's heap, so in the kernel space there is some space that is static, which is for kernel's code and data, and then above that all the other area is where I am going to allocate a page and create this mapping for the user process so that the user process can implement its own address space, right. So there will be all the user pages will have two mappings, one which will be the user's mapping so the user can access it, and one which will be the kernel's mapping where for kernel to do its own bookkeeping, right. Of course the user can only access this page through its user address, the user will not be able to access the page through the kernel address because the kernel address is protected, it's privileged, right. Okay. So by ensuring that only the pages which belong to the user are ever mapped in this area, the kernel basically ensures that the user cannot touch any privileged memory, or the process cannot touch another process's memory, all right. Also we said that if once again if a process needs to make a system call, then some code here is going to execute the interrupt instruction. Let's say it says int some number which indicates the system call number. On Linux it's the hexadecimal 80 number. So interrupt hexadecimal 80, what it's going to do is it's going to go through the IDT and it's going to transfer control to an EIP somewhere here, and that EIP should be the handler for that particular system call, right, or the system call in general. The user can give arguments to the system call by setting up its registers in a certain way. For example, the first register can say what is the name of the system call, right. So you can say that, let's say the fork system call is number 1, exec system call is number 2, and so on, and that way you can basically set it up to say that this is the name of the system call, and other registers can say give arguments, right. So integer arguments can be just given in registers. For example, ECX can contain the first integer argument, let's say file descriptor. But if I was supposed to give any string, let's say the exec system call takes a string argument, right, and a string can be pretty large and registers are not enough to hold a string. So the way to do it is basically the string is going to live somewhere here, right. So let's say there is a file called foo and the string called foo is living here, and so what the user does is he sets up the value of the pointer which points to foo as a first argument, right, in the register, let's say ECX. And so the kernel looks at that pointer, and because the kernel has the same page directory mapped, so the same address space is mapped, when it dereferences that pointer it can read the string foo, right. So this is important to understand. When the user makes a system call, it is possible for the user to actually give pointers to the kernel to specify its arguments, right, and the reason the pointers work is because the kernel will execute the system call in the same address space as that of the program, right. If the address spaces were different, then pointers couldn't have been passed, okay. So this is a huge optimization. I mean this is a big advantage of doing things in this way as opposed to doing things in a way where you were using segmentation, for example, because segmentation will change the address space for the kernel, or using a separate page table for the kernel, right. So often you may have wondered why I am eating up so much of space for the kernel in the virtual address space. That way I am basically squeezing out the process, right. A process could ideally have had as big as a 4 gigabyte space on 2 to the power 32-bit machine, but now these kernels like XV6 or Linux or whatever else is basically constraining the process to live only in 2 GB, right. But there is a big advantage to doing that. The advantage is that the user and kernel can now talk by pointers. If I want to communicate some information, I can just pass a pointer and that pointer works. If the kernel can also reply by setting some value in the address space of the user and give a reply. On the other hand, if the kernel had a separate address space, then pointers wouldn't have worked, right. Okay. So yes, question.
Sir, if the physical space is supposed to be 2 GB, then can I allow a process to occupy a virtual space of greater than 2 GB? Like if it were different also. If the stacks were different, if suppose my physical memory is only of 64 MB, so can I allow my process in my virtual memory to occupy space more than 64 MB?
Okay, so the question is, if my physical memory is small, then can my virtual address space of a process be larger than the physical memory? And the answer is yes. Why? So you can make pointers first of all. So the virtual memory doesn't need to be contiguous. It can have non-contiguous mappings. So even though the physical memory is contiguous, the virtual address space is non-contiguous. So some pages are mapped, some pages are not mapped. Also, you can map the same. A user process could very well say, I want these two addresses to map to the same physical page, right? So you can basically say you can have aliasing. So although it's not very useful to have two virtual addresses pointing to the same physical address in the user space itself, but it's possible to do that. So in any case, so I mean, to answer your question, it's possible for the virtual address space to be bigger than the physical address space.
Then sir, in this case, like we already know that the physical space is not crossing my 2 GB. So how is the kernel in my virtual space is restricting my user?
Okay, so the question is, I mean, if I assume that my physical memory is never going to be greater than 2 GB, then this organization makes sense, right? But in real world, that's not true, number one, all right? So physical memory could be greater than 2 GB, and still I'm restricting my process to have only 2 GB at most, if you're using XV6. If you're using Linux, you are restricting it to 3 GB, right? That's not a great idea, great design. I mean, today we have memories of 64 GB, even 128 GB. So restricting that a process can only access 3 GB basically means if I want to actually write a program that needs that much memory, I need to have a set of processes if I'm executing on 32-bit machine, right? On the other hand, if I'm executing on a 64-bit machine, this problem gets solved automatically, right? Okay. Yes.
Since anyways there are for every address in the user mapping there are two corresponding virtual addresses which map to the same physical address, that is one in the kernel and one in the user. So as in so if there wasn't a separate so if kernel wasn't living in the user address space, if kernel was living in a separate space, but suppose and it had to, and the user had to make a system call, so couldn't there be a mechanism in which the user could have passed a pointer which contains the kernel mapping instead of its own mapping?
Okay. Okay, so the question is, couldn't the user, so I said that the user can pass pointers to the kernel, it can set up some area in its own memory, it can initialize some values in its own memory and use the address of that memory location and pass it to the kernel, and the kernel can dereference it, and because the kernel is executing the same address space, it is okay to dereference it. And the question is, if the kernel was executing in a different address space, could the user have figured out what the pointer is in the kernel's address space to the location that it has set up and pass that value to the kernel? That's very difficult, right? How will the user know what is the value of the kernel's pointer in that address space, right? So you need some interface to basically be able to communicate that, and if you have to do it for all the addresses in the user space, that's very costly also, right? So these are interesting ideas, questions, and something to think about on your own for some time, and then we can discuss about it more, right? So a lot of thought has gone into what's the right operating system design, and so the mainstream kernels that we use today have taken this design because of its efficiency, right? Because the communication between user and kernel is very fast, just exchange a pointer, right? And that makes things, and speed is by far has by far been the most crucial factor in deciding a design. There have been other operating systems which are actually popular, not necessarily in the mainstream desktops and space and server space, but maybe in the embedded devices space, where security is more important, for example, right? And those kind of organizations are what's called microkernels, right? Here the idea is that the kernel subsystems live in separate address spaces, and so this gives them very strong isolation from each other, right? So for example, there will be one process which is the system call handler, right? And so if you want to make a system call, what you do is you just pass the arguments, but now you need to copy your arguments from one address space to another address space, and the other process which is doing the system call handling is going to read those arguments and then execute it, right? So these are all organizations, but I mean there are pros and cons. If you basically divide the kernel into separate address spaces, it gives you very strong protection, isolation, but it decreases performance, right? So that's the trade-off. Question?
In case of P1, suppose it uses kalloc, the kernel allocates makes a page and allocates it to foo, right? So sir, that process, that physical address will be mapped in user space, and it will also have a mapping in kernel P. Sir, but how will the kernel of P2 will know that where is that mapping, because we are not actually updating the page directory of P2, right?
Why does the kernel of, I mean, so firstly there is only one kernel, right? It doesn't mean there is no kernel of P1 and kernel of P2. It's one kernel which is mapped common. Yeah, let's say if you are working in the address space of P2, then why does it need to know?
Sir, because next time suppose P2 asks to allocate for another page, how will it know what space has been used?
Alright, so these mappings in the kernel side of things remain even in P2, right? These mappings get removed, but these mappings still remain, and these allocation data structures also remain. So it knows that this area has been allocated already.
Sir, but suppose when the P1 was running and it asked for kernel to allocate a page, it allocated a page and updated its entry, the free, it has updated its free page.
Right, and so the data structure, the free list itself is living in the kernel space, right? Okay.
Sir, but, okay, it was shared.
Right. So the free list itself is in the kernel space, and so even if you switch to P2, the free list remains just where it was, right? So all the data structures to do all this bookkeeping are living in the kernel space, and because kernel space is shared between all the processes, you basically have you don't, information is not lost. The kernel's information remains. Question.
So user pages are allocated from kernel heaps. So why in a system like Linux, why do we need 3 GB for user address space and only 1 GB for kernel address space?
Okay, very interesting question. If the pages in the user space are allocated from the kernel's heap, then shouldn't the kernel's heap be necessarily larger than the size of the user space? Really? So does it need to be larger? Because as we said that the address space can be bigger, the actual allocation size can be smaller. So you only say, let's say the address space of the process could be 3 GB, but the allocation size could be, let's say, only 5 MB. If you wanted to make larger allocation sizes, let's say greater than 1 GB or 2 GB, then as we said before, x86 is a very simple operating system which requires that the entire physical memory is mapped in the kernel address space. But modern like full operating systems like Linux or anything else is basically going to not going to map the entire physical memory in its address space. It's going to recycle the address space and make it point to different regions, and it's going to do bookkeeping at the physical page level, that which pages have been used and which have not been used. Right? So it's not necessary. x86 is an example of an operating system which requires that the entire physical space is mapped in the kernel address space, but that's not necessary. Right? It makes things simple, and that's why we are discussing it first. So we have already seen this. There's an interrupt descriptor table that has CS:EIP pointers. CS has the last 2 bits as 00, which means it runs in privilege mode, and EIP is somewhere in the kernel's code region, so the handler gets called. Right? And these pointers which are initialized, these are initialized by the operating system itself, and we have already seen that the user is not allowed to overwrite either the IDTR, which points to the IDT, or the entries in the IDT itself. So the IDT itself is going to live in the kernel space, so clearly the user cannot access it. If it was able to access it, then it can just bring down the system. So let's look at how a system call works. Right. So let's say this is user space, and this is kernel space, and this is a process P1, right? And in the kernel space, every process has a stack. Now let's assume xv6 is processes model, so every process has a separate stack, kernel stack, P1's K stack, right? When the process makes uses the interrupt instruction to make a system call, immediately the stack shifts, the stack starts pointing to K stack, right? And the hardware pushes some things on the K stack. What are those? Let's say CS, EIP. These are users CS, right? Users EIP. Whatever was the old CS, whatever was the old EIP, E flags. So whatever were the values of these registers before the interrupt, SS and ESP, right? And so these get saved on the, so let's say this was top of the K stack. So now the new ESP points here, right? So let's say this is users ESP. So that's what happens immediately after you make a system call. As soon as the interrupt instruction is executed, the state of the architecture starts looking like this: CS, EIP, E flags, and stack has shifted. So whatever was the user stack, that is of no consequence. It has just been saved. Whatever that's represented by ESP, and this ESP must necessarily be a pointer in the user's address space. Similarly, this EIP must necessarily be a pointer in the user's address space, right? Okay. So now the handler gets called. So at this point, the handler gets called, and the first few things it's going to do is it's going to say, execute instructions like push other registers. Let's say push EAX, ECX, you know, other segment registers, let's say SS, DS, and so on, right. So it's going to push all these registers, and so eventually, at some point, ESP is going to come here, and you're going to have, let's say, users EAX, and so on the stack, right. So the kernel stack is a nice place where you can save all this information about what were the values of the user registers at the time of this interrupt instruction, right. And so this entire structure is called the trap frame. It contains all the registers that have been saved by the handler, and it contains all the registers that were saved by the hardware, right. And this trap frame is important. So the reason it's called a trap frame is because it's a frame that is initialized on every trap, right. And the reason it is important is because from here, the kernel functions can figure out what were the values of the user registers at the time of the interrupt system call. For example, if it wants to know the arguments, it just needs to look into the trap frame. Also, the return value can be passed through the trap frame. If I want to pass the return value in the EX register, then all I need to do is just overwrite the trap frame EX, right. At the time of return from interrupt, this trap frame will get popped in the same order in which it was pushed, in the opposite order in which it was pushed, and so first few values will get popped by the software, and then the irate instruction is going to pop the last 5 values, and the user will continue as though it never went into the kernel, except that the return value would have changed, and maybe some other things would have changed depending on the semantics of the system call. Okay. All right. So basically, if I were to draw the K stack at any point, it will initially have the trap frame, right. Then it will have some other whatever function call chain within the kernel, right. So the handler will push all these registers, and then it will maybe call some function, right, depending on what vector it was. For example, it will call the syscall function. The syscall function will read the first argument, and let's say it was the exec system call, so it will call the exec function or something, right. So all these functions, their function call frames are also saved on the stack, right. So you basically keep pushing this stack like this, right, and at some point you would have handled the system call, which may involve overwriting values of the trap frame, and then you will start returning from the function just like you return from normal function calls, right, and at some point you will return from the trap frame, return from the kernel to the user, and so the last function that should get called is a function that pops off the trap frame and then calls irate, so to return to the user mode, right. So on x36, this function is called the trap rate function, right. So in other words, what should happen is that whatever is the function call that you got called, the last return address should be trap rate. So when the last function returns, it should return to trap rate, and trap rate will basically just pop off all these registers and then call irate to return back to user mode, right. So the stack does not only contain the values of the registers, it also contains the values of the instruction pointers that should get called and in what order, right. Well, the stack basically acts as a function stack, and so every time you return, you basically pop off a value from the stack and jump to it, right. So if your stack contains a reference to trap rate, then when you return from the function chain, you are going to next execute trap rate, and trap rate is going to do all this for you, and then you're going to jump back, right. So in other words, the K stack, the kernel stack of a process, contains enough information to say where should you start executing and what all should you execute next and with what values, and eventually it should typically just go back to the user after it has finished execution, all right. Okay. Yes, question. Okay, the question is, will trapret pop the entire trap frame and then call iret? No, trap frame will pop only the registers that were saved by software, right, and the last 5 registers will be popped by iret. Okay, right. So the important thing is that the entire information about the kernel side execution of the process is encapsulated in the stack, K stack, right. So let's say a function wanted to call the yield system call, right. So far we have seen a system call that winds the K stack and then unwinds the K stack and then returns to the user mode. But yield system call is a call which requires you to switch the process, right. It's basically saying I don't want to run anymore, let somebody else run, right. So yield is an example of a system call which will enter the kernel on P1's K stack but exit the kernel on P2's K stack, right, and in the middle this switching of stacks is what's called a context switch, right. So basically when a process calls yield, let's say P1 calls yield, P1's K stack will get formed, the entire chain will get saved on the K stack, and at some point it's going to say, okay, let's switch the stack, right, and so you're going to go to P2's K stack, you're going to go to P2's K stack, and instead of unwinding P1's K stack as in the previous example, I'm going to unwind P2's K stack, and when I unwind P2's K stack, and also I'm going to change to P2's page directory, right. So this was P1's page directory. So what happens? So this process of shifting from one process's K stack and one process's page directory to another process's K stack and page directory is called a context switch. So you change the K stack from P1 to P2, you change the page directory from P1 to P2, and then you just execute on this K stack, and then when this K stack gets unwound just like before, so by returns, you actually end up in P2 exactly as it was executing the last time it got preempted, right. So what has happened is this K stack will get saved in memory, right. So this K stack will get saved and this K stack will become active. At some later point, if let's say this process calls yield and then it wants to shift to this K stack, all it needs to do is change to this K stack, change to this page there, and now this one will get unwound just like it would have gotten unwound even if there was no context switch, right. So that's how a context switch works. One process makes a system call, you execute in the kernel, you form some state in the kernel which is saved in the K stack, you switch the K stack, you switch the page directory, you unwind the K stack of the other process, and you are back, you are suddenly executing exactly as you left the other process in some previous iteration of this procedure, right. So the page directory of a process and the K stack of a process contain the state of the process, the running state of the process as it was left the last time it was context switched out, right. So this process is called switched out process, right, and this one is called switched in, right. So the kernel maintains a list of all the switched out processes. The scheduler picks one of those switched out processes, and a switched out process must have a K stack and a page directory. You switch to that K stack and you switch to that page directory, and you are now running in that particular process's mode. So that's how a context switch happens at the process level.
So that list is PC.
Yeah, so this list of this list which contains all these process state is basically the list of PCBs, right. So typically the process control block will have pointers to its K stack and pointer to its page directory, right. And so there is a list of PCBs. So there is a list of PCBs, and the scheduler will pick one PCB and then switch to its K stack and its page directory, and and that's it, that's a context switch. So all the information that was necessary to encapsulate the information exactly where that process got context switched out is available in the K stack.
So why can't we save the pointer to the page directly on the stack?
Why can't we save the pointer to the page directory on the stack? Okay, that's a very interesting question. Can you not? Well, actually in theory you can, nothing stops you. You just have to make sure that it never gets overwritten, right? Recall that when there's an interrupt, immediately you switch to K stack and things get pushed on the K stack. So you have to make sure that the top of the K stack that you initialize, that you put it inside the TSS, the task state segment, is not such that you ever override that page directory. So you can use one, the top +1 area to basically contain the page directory also, right? Is it a big win? Perhaps not, because I mean, what have you saved? You're still using the same amount of space overall. You could have saved it in the PCB, you're saving it in the stack, perhaps complicating things a little bit for yourself, right?
So since the different processes share the same kernel space, so the case same kernel mappings, so the kernel stack is also same in both.
Okay, so here's the interesting thing, because each process has the same mapping of the kernel everywhere. When you context switch the page there, it's okay, right? So the nice thing about this this picture here is that in this context switch, when you shift it from P1's page there to P2's page there, because you are executing in kernel mode and the kernel is mapped identically in all the address spaces, there's no problem. It's not like the EIP has changed or the ESP has changed or the contents at EIP have changed or the contents at ESP have changed. All the values currently are kernel values, and even if you change the page directories, you're okay, right? You couldn't have done this, for example, if you were executing in user side, right? Because you have different address spaces. The moment you change the page there, your EIP will no longer be valid, the next EIP, right? But that does not mean that they have the same page there, right? I mean, it's the same space from which they have allocated different regions for different processes. So one case, in the same K heap, there will be one page for P1's K stack and another page for P2's K stack. There will be yet another set of pages for P1's page there, right? And yet another set of pages for P2's page there. These have to be completely disjoint structures, right? It's in the same space, but they have different areas that have been allocated for different processes. Okay, good. Okay, so we've seen how yield works, right? And yield is an example of a process saying, I want to give up the CPU, I want to be a good citizen, I want to give the CPU to somebody else. But we also said that if a process is not yielding the CPU and the process is not obliged to yield the CPU really, then the OS should have a mechanism of taking away the CPU from the process. And the way to do that is the timer interrupt, right? So we said that the OS can, there's a device called a timer in the hardware, and the OS can configure its frequency, can say that fire every X number of milliseconds, and so each time the timer interrupt fires, it has the same effect of an interrupt, right? So once again the IDT gets consulted and the appropriate handler gets called. Earlier it was the syscall handler that was getting called, this time it will be the timer handler which will get called, let's say. Right. Once again, the mechanism will be identical. So instead of interrupt 0x80, let's just say an external timer interrupt occurred. Right. And once again, P1 will shift to K stack, and it will push all these values on the. So these 5 values will be pushed by the hardware. Other things will be pushed by the timer handler. And now it will call the scheduler, right? And it will be the identical thing. I mean, just like yield, I mean, the only difference between a timer interrupt and the yield system call is that a timer actually forced the preemption, yield was a voluntary preemption. The mechanism is identical, right? Once again, the K stack will contain all the information about exactly where the process got preempted and what were the values of its registers in the trap frame. right? And the kernel will execute whatever is the kernel's call chain, that will also get saved in the trap frame, and then you context switch just like before, right? You will context switch, another process's K stack would be saved. The other process may have been preempted by a timer interrupt or may have been preempted because of a yield call. In either case, the unwinding process is similar and you go back to the user, right? So that's how an involuntary context switch happens. The previous case was a voluntary context switch where somebody called yield. This is an involuntary context switch where a timer interrupt occurs and the scheduler decides that you need to be switched off because you've been running for long.
So the handlers are same for both?
Are the handlers same? No, I mean they are roughly calling the same functions at the end, but initially they are slightly different. Okay, one is a system call, one is not a system call. Okay. All right, very good. So now we understand how timer interrupt works. Let's say a timer interrupt occurred and the scheduler decides that it does not want to context switch. That's a possibility. No problem. You will not switch the stack. You will just unwind the same stack again, and you are back where you were interrupted. All right. So one question that you may have is, you know, this whole business of actually a timer interrupt coming and you know, this kernel code getting called is an unnecessary nuisance if there's only one process that's going to run. You know, let's say you're running some high performance computation, you have written some very fancy program and you're running it, and you know it's the only program that's running in the system, and now this timer interrupt comes and bothers you every time, and only for the scheduler to say, oh, this is the only process running, and I'm just, you know, I just wind the stack and then unwind the stack, and what is the overhead of this, right? So the overhead depends on what? On the frequency of the timer interrupt, right? How fast is the timer interrupt occurring? So, so let me just first tell you, you know, what kind of numbers are there. Let's say 10 milliseconds to 100 milliseconds is the duration between two timer interrupts, right? So, or 10 to 100 hertz is basically the frequency, typical frequency that you use for your timer interrupt, right? On modern machines, one instruction. So this is timer interrupt. This is 1 by timer interrupt frequency, right? So let's say 10 to 100 hertz. All right, and this frequency, and how long does it take to execute one instruction on a modern processor? Let's say, you know, 2 point some gigahertz or whatever. So it's, you know, roughly on the order of 1 nanosecond. So how many instructions can execute in one timer slot? Let's say 10 to the power 6 to 10 to the power 7 instructions, right? Or let's say 10 to the power 5 to 10 to the power 7. Even if you want to be, you know, if you want to say that memory access is going to take a lot of time, you know, memory is not so fast and whatever. So 10 to the power 5 to 10 to the power 7, right? So that is the number of instructions that get executed, roughly speaking, in one timer slot. What is the overhead of one timer interrupt if you were not going to context switch? It is, you know, one switch into the kernel, executing a few function calls, returning from a few function calls, and going back. How many instructions do you think will get executed in doing this? So somebody says 100. 20? Okay, let's say, you know, 1000 is, you know, a very conservative number. So 1000 instructions. So that's basically, let's say 10 to the power 3, right? So the overhead is something like 10 to the power 3 upon, you know, very conservative figure, 10 to the power 3 upon 10 to the power 5, that's 1%, right? Actually it's going less than 0.1%, you know, actually, you know, so this is 1% of course, but roughly the overhead is less than 0.1% of doing this timer interrupt on modern hardware, right? Okay, of course, you know, you may say, oh, but so what happened in the early days, you know, so we right now have 2 gigahertz machines, let's say not too long back, let's say 20 years back, we had only 100 megahertz machines maximum, right? So when you had 100 megahertz machines, this overhead may have increased because the number of instructions you can execute is smaller in a time interrupt. But then you also used larger values of the frequency, let's say 100 milliseconds. In fact, you can safely decrease the timer interrupt frequency from 10 milliseconds to even 1 millisecond and still not see any overhead, right? But there is no real advantage of doing that, and exactly why what other factors go into deciding what the timer interrupt frequency is are we going to discuss as we go along the course.
So can't we change the frequency based on the number of processes running? We already have the information how many processes are running, so we can reduce or increase the frequency accordingly.
Okay, shouldn't the timer interrupt frequency depend on the number of processors that are running? Okay, so mostly why no?
Thank you. So because it's up to scheduler to.
Firstly, let's understand that this timer interrupt is being generated per processor, right? So every processor has a separate timer device attached to it, in theory, right? How it works in physical hardware is a different thing, but let's just assume that each CPU has a separate timer device attached to it, right? Each CPU is doing its own scheduling basically, right? And of course the scheduler is a common scheduler that understands that there are many processors in the system, and it basically chooses whether this process is supposed to run on this CPU or not, etc. Right? So every CPU has one timer device. So I mean a timer interrupt frequency should really have no relation to the number of CPUs in the system, right? In fact, each CPU can have a different timer frequency, for that matter. Does it make sense? Maybe not, but it's possible.
So won't it become hard to then synchronize all of these things?
Wouldn't it become hard to synchronize all these things if each of them had a different timer interrupt frequencies? What do you mean by synchronize?
Like one of them is working at 10 milliseconds and other is at 9 milliseconds. So when I
Okay, so the question is, do these processors need to be synchronized? Is it necessary that each processor gets a timer interrupt at exactly the same time and comes back exactly at the same time? No, not at all. Right? So this processor could be executing, could get a timer interrupt now, and another processor could get an interrupt 9 milliseconds from now. Perfectly okay. Doesn't matter. Right? They don't need to be synchronized with each other. In fact, synchronization will be very hard to implement in hardware. That level of synchronization is almost impossible to achieve. Okay, so they don't need to be synchronized. The timer interrupts are separate. They act as completely asynchronous devices. Okay. Finally, I gave you an example where the timer interrupt occurred while the process was executing in the user mode, right? So I gave you an example where I said, okay, let's see, right? So I gave you an example that P1 was running, and the timer interrupt occurred in the user mode, right? And so all this started happening after that, right? But can a timer interrupt occur while the processor was already executing in the kernel mode? Yes, why not? I mean, the timer interrupt has no idea whether you are executing in kernel mode or not. It's possible for the kernel to disable interrupts while it's executing in the kernel mode, but on XV6 it doesn't do that, right? So while the processor is executing the kernel mode, a timer interrupt can come, in which case the things will not be like this, right? What happens if a timer interrupt comes in the kernel mode? You don't need to switch the stack, and you don't need to push these extra values SS and ESP, right? So if you were executing, let's say this was the K stack, and let's say this was the ESP while you were executing in kernel mode, and a timer interrupt comes. Let's say there's a timer interrupt, right? So what will happen is ESP will just get decremented, and CS, EIP, and E flags of the kernel at that time will get saved, and the handler will get called just like before, right? So it's possible that a kernel's execution gets interrupted, in which case the kernel's EIP gets saved, right? And all the other registers will also get saved just like before. So all kernels, EAX, kernels. So this time you're going to save kernels, EAX, and all the other registers on the stack, right? So you're going to save all these things, and then you may want to call the schedule function just like before, right? So the only difference between the previous case was that you started at the top, and all the values that you were that you were saving were users values. In this case you don't start at the top, you start at wherever you are currently, and whatever values you are saving now are actually kernel's values, but everything else remains the same. You are still going to call the scheduler may again attempt to do a context switch, but that is okay, because what will happen is a context switch will happen and this kernel stack will actually have 2 trap frames in it, right. So if a timer, let us say timer interrupt received in kernel mode, and let us say you context switched, then what will happen is this was P1's K stack, you will have user trap frame. After all, if it was executing in kernel mode, it must have come from the user at some point, so the user's trap frame must be there, some function called chain, and then it got trapped again, and so this will be the kernel's trap frame. Right, and at this point let us say it decides to context switch, so from here it just context switches to another process P2's K stack, just like before. If ever it comes back, it is going to unwind the stack. Once again the kernel's trap frame is going to have a trap rate here, so it is going to return to the trap rate function, it is going to return from the kernel trap and resume execution at exactly the same point where it was interrupted in the kernel, right, and now it will execute again in the kernel even after returning from the trap, and then it will again do trap rate and then go back to the user, right. So it is possible for the kernel stack to have 2 trap frames, right, one for the user and one while it was executing the kernel it got interrupted again, let us say. Okay, let us stop.